For today is going to be on the 802.11. So that's the Wi-Fi. So we'll discuss first the general standard for communication for the Wi-Fi, how the system is standardized, and then after that we'll move to the security standards in Wi-Fi. Just to give you a general idea about how standards work, how it defines the different functionalities within a particular system, whether it's for general communication or for specifically the security aspect of the communication system. The 802, just this slide is just introductory, gives you a bit of a history on the 802.11. So the 802 is the committee which is developing standards for local area network in general, whether it's wireless or wired, right? So the Ethernet, for example, if I remember correctly, was 802.3, which is part of the same standardization committee, but a standard for a different type of network, okay? And also there is the 802.11, which is for the Wi-Fi. The name Wi-Fi, by the way, did not come from the IEEE standard. There is another body of, not standardization, but another body of alliance called the Wi-Fi Alliance. This alliance is a group of industrial partners who are big industries in the area of wireless local area network, and they formed that alliance just to make sure that they ensure interoperability between their products. So they want, if I create a card and you create an access point at your company, my card should be able to talk to your access point and vice versa. We don't really need to manufacture everything closed, make it open, which is part of what the standardization does. So you will notice later on that there are many aspects of the communication system in the Wi-Fi and the security system that has more than one name. And the reason for that is it's the same standard specifications exactly, but has been given a name by the 802.11 committee and has been given another name by the Wi-Fi Alliance, but it's exactly the same standard. We'll come across a few of those as we go through. Before going into the details of the Wi-Fi standardization, the 802.11, from a communication and from a security point of view, remember early on, we discussed something called the layered model for security, right? And if you remember those three important layers for security, anyone remembers them? Threat to attack were one layer. What was the other? What are the key pillars of any secure system? Not the pillars of security, the pillars of the layering system. So there is a threat, there is a service, which is the action done by the network to combat the threat, and there is a آخر حاجة method or algorithm, زي for example when we talk about the encryption technique, specific encryption technique and so on. So there is the threat, there is the service, which is the thing provided by the network to prevent the threat, right? And then how it's done, the third one was the mechanism or the algorithm or whatever of those alternative names, right? So similarly, at that point, it was also an ISO model, by the way, right, for the security. Similarly, I told you at that time there is something called OSI, the Open System Interconnect, which is a layered model for the general operation or the general functionality of any communication system, okay? Whether that communication system is wireless or wired, okay? These are the ones that we see on the right side here, right? There are 7 layers, okay, defined in the ISO Open System Interconnect, starting from the lowest, which is called the physical layer, with different names here, until we go to the highest, which is called the application layer. Why did they actually come up with something like this? Why did they define several layers for an operation of a communication system? Okay, the reason for this is from an engineering point of view, if you go for each one of those components, which is called a layer, and you define what functionalities needs to be performed there, and what are the two interfaces, it's interface to the layer below it, if there is any, and its interface to the layer above it, if there is any, right? Then you can get a group of engineers or developers to work on this without really any need to talk to the other groups, because they know what's the function that they need to do and what is the output, how it should look like, the output that should produce. That's the interface to the upper layer. And what input they should expect, which is the interface to from the lower layer, right? Okay. So if you define those three things, input, output, and the functionality required, you can get a group of engineers to work on that without really any dependency on people who are working on the other functionalities, okay? So that's why they break the functionality of any communication system into those different layers. In the next slide, I'm going to describe quickly what each layer is responsible for, what kind of functionality is being performed at each layer, or what part of the communication system is described in each layer. But here, as I mentioned, just the objective is to show you the different layers and to tell you what is contained in each layer, functionality, interfaces above and below, okay? Now, one more thing is easier to describe here. Whenever you want to perform, for example, something like searching a web, okay, from your computer or from your laptop, once you put the command on the interface of the computer, the flow of the data is gonna be from the user going through this layer, and then from this layer to this layer, from this layer to this layer, from this layer to this layer, and so on, right? All the way down, and then through the system to some server somewhere, right? And then if you get a response, the response from that server is gonna be in the opposite direction, right? All the way until you get the output that you are expecting to get. So you put a command typing the address of a web page. This is basically, it's translated to sending a request for the server of that page to show you the first page, okay? And then that command is translated from the application, in this case, is your web browser. So it's translated by the web browser into something which is suitable for the presentation layer, and then it's translated into something which is suitable for the session, transformed into something suitable for the transport layer, and so on, until it becomes physical signal on the cable or on the wireless medium, and then it reaches the other side. On the other side, of course, there are 7 layers, so it goes all the way up until you get some response. That response is gonna be sent back to you, and then you get it all the way until you can see it in your application, okay? So that's how the flow goes on, okay? Now let's look at what these layers are about. And the following figure is actually borrowed from this website. It's very nice, very elaborate figure, shows you the different layers, starting from the lowest, which is the physical, that you see on the right side here, and going all the way to the application layer. Yeah, I didn't update the slides on the, sorry. I will update this, okay, sorry. Yeah, I added only like 3 slides, this and the 2 before it. They were not there, so, okay, good catch. So if you go to that web page, by the way, you can also get more information, not just these brief descriptions, but it will give you more details about what's on each one of those layers. But as far as we are concerned here, I only want you to know that there is a layering model composed of 7 layers, and just quickly to understand what each layer is responsible for, okay? So the physical layer, starting from the lowest one, the physical layer is responsible for the physical properties of the communication medium. So it talks about, are you using a cable? Are you using wireless? If you are using a cable, what are the dimensions of that cable? Is it coaxial? Is it 2 pairs line, twisted pair? Is it fiber optic? What are the dimensions, and so on? So that's one part related to the communication medium itself, wired, wireless. If it's wired, there are more specifications to the communication medium. And the other aspect handled by the physical layer is the physical properties of your signal. So what electric voltages are there if it's on a wire, right? What's the limits of the voltage? How does it vary? Does it vary like a sinusoid or a square wave or whatever, okay? And frequencies used. So if you are sending over 2.4 giga, over 1.6, over 5.2, over 900 mega, all these frequencies and so on are specified as well on the physical layer. So the physical layer is responsible for everything that has to do with the physics of communication, okay? The medium, the dimensions, the geometry, the different properties of the electromagnetic signal and so on, okay? This is the physical layer. Data link layer is responsible for identifying the methods that are required to establish reliable communication from one point to the other only. So between 2 points, right? What do you need to do for your information to make sure it's reliably communicated on one way or the other, okay? This is the data link layer. So what is entailed there? Something like adding some bits for error control. So you can detect, for example, the existence of error, or maybe even correct those errors, okay? Or formulating your data rather than just being bits one after the other. Here, we also do something called packetization. So we formulate our data into group of bits, and then we add to those group of bits some extra information that allows us to reliably transfer that amount of bits from one location to the other. This unit is called packet. Okay? And that packet is formulated in the data link layer. So that's part of the functionality of the data link layer. Also, the data link layer is responsible for something called medium access control, saying at any point in time who gets to talk and who has to stay silent and listen only. Okay? So that's part of what's handled by the data link layer. Okay? Any questions so far? The next layer is the network layer. Now things becomes a little bit more complicated. When you have multiple nodes, right? And they might be connected by any shape of a network, right? Maybe something like this. Okay. And maybe another line here. Okay. So you have, and you want to communicate, for example, from this to this. There are probably multiple ways to go to send your information. It can go, for example, from here to here and then here. Or it can go down here and then up and then here. Or it can go to this and then this and then this, right? There are multiple possible paths between a start point and an end point that are trying to talk to each other, right? Figuring out which way your data should go, which is called the routing functionality, is the key function of your network layer, okay? Wi-Fi standards is discussing things up to this level only. So the standards of the Wi-Fi defines how the physical layer looks like and how the data link layer looks like. Has nothing beyond that. So it's up to establishing a point-to-point successful communication. Okay. When you want to do things like these, you need to go at upper layers. You start using, on top of your Wi-Fi, you use something like IP network, right? Which is the most common way to access the internet, right? So that protocol, which is the IP networking protocol, defines things above the data link, which is the networking, and in particular, it's responsible for making sure that you move your data from one source to the destination through multiple alternatives, how to select which one, okay? So that's the IP level. Now, the next level has to do with the fact that we agreed that we are going to divide our data into pieces called packets, right? Which is done here. Now, if I want to send a full message would be something like a full file, or a full picture, or a full document, right? So it's not only one packet, because a document is much larger than the bits that I will put inside my packet, right? So a group of packets, how many depends on what is your total message size, okay? A group of packets that contains a complete set of information, like a full image, full document, full page, full video, voice, whatever, okay, is called a message. And inside that message, okay, if you want to reliably communicate that message, there are other aspects that you have to consider other than just selecting the route. What aspects? A message is composed from multiple packets or of multiple packets. Now, what happens if, for example, let's say this is my network, okay, and it's connected this way, for example. And then to communicate here, I have this path. I can send packets here, or I can send packets here, right? In both ways, I can transmit from this to this. Now, at some point, I was sending the first couple of packets. They went actually through this path, which is a bit longer. And then the third one, I found that this path is no longer available, and it's actually faster or cheaper or whatever to send it across this one. So the third one was sent across a shorter path. There is a high possibility that the third will arrive before the second, for example. Okay? So now at the receiver, you get 1, 3, and then 2. If you put it and you keep it this way, and you try to look at your full message, right? You will not. You will see something scrambled. You will see something which looks to you as a garbage, right? So how do you do that ordering? That's part of what the transport layer is responsible for. So the transport layer has two important functionalities: ordering of packets so that you receive a correct full message. That's one functionality. And the other one has to do with the practical aspects, which is also very important. Okay. Now, if at the receiver side, I am a bit slower, right? So my receiver is an old computer, which is a bit slower in terms of its ability to receive packets one after the other. While the transmitter, which is, for example, Google server, is much faster. So if I get the information at the speed of the faster transmitter, at the receiver, my memory will fill up before I was able to process everything, and I will start losing part of the information because there is no way, no place to store that information until it is processed and displayed, right? So now there has to be a way between the receiver and the transmitter to coordinate, to say, please slow down. Don't send me too much information. This is called congestion control. Okay? Congestion comes from congested, right? A congested system is a system overloaded, right? So in order to do that congestion control, that functionality is handled also within the transport layer. So two important things: ordering to make sure things arrive in order. If they don't, you should be able to reorder them so you display them in order. That's one. And the second thing is, the second important functionality of the transport layer is congestion control, making sure you have matching speed between the transmitter and the receiver. Otherwise, you might lose some information. Okay? If I am, for example, myself, I'm a bit slow in understanding things. If I'm someone like what I'm doing to you sometimes, talking very quickly and like going through slides very quickly, you will start, as a student, you'll start losing some information because you cannot follow up, right? So in that case, you raise your hand and you say, please slow down or repeat that part or whatever, right? So that kind of coordination between communicating nodes is handled by the functionality of the transport layer, okay? Up to here, these are the essential layers that exist in our day-to-day communication. So any access to the internet, anything that we do related to the internet uses those 4 layers, right? Physical, you start by, for example, communicating through the Wi-Fi that defines a certain physical layer property, and then controlling the access. Who talks to the access point is handled by the data link of the Wi-Fi, and then figuring the right route is handled by the IP, and then the transport, which is controlling how to order the packets and congestion control, is handled by TCP, Transport Control Protocol. Hence, you hear the name TCP/IP. These are 2 protocols combined into the internet functionality. One of them is doing the transport layer, the TCP, and the other one is doing the routing for the network layer, which is called the IP protocol, okay? After that, we start talking about applications running on your computer, the type of communication that you like to establish. So we call those 3 the higher layers, okay? What is entailed into those 3? The session layer is particularly there to handle certain situations where you need to have an end-to-end continuous connectivity. When does this happen? When, for example, you are using your WhatsApp to do a voice call, okay? That's a data application, but that data application is establishing an end-to-end connection, okay? So it will stay, that connection will stay, the call will stay up until you finish with the other party, or you use Zoom, or you use any of those live end-to-end session requirements. This functionality is had so to establish a continuous link. It's a logical link. It's not an actual physical link, okay? Just logically, there is an open call between you and the other side. But on down there in the internet, it goes through different lines with different cables, where every part of your voice might go through a different line, but the end is the feeling from your side is you have a continuous maintained communication. Okay, that continuity is maintained by the session. To establish and open a session, keep it alive until I finish what I need to finish, and then we hang up, so the session is closed. Okay. The next level is presentation. Now, presentation has to do with upper layer things that you need to do with your data. For example, to secure the data, you need to perform encryption. Encryption is handled, encryption and decryption, okay? Is handled by the presentation layer. If I have a bit of a slow system, but a large amount of data that I need to send over that system, I might need to do some compression of the data. So at the transmission, rather than sending my data as is, I compress that data, becomes smaller, takes shorter time to be transferred, and then the receiver will decompress it again. So that functionality of compression and decompression is handled also by the presentation layer, okay? These are or translation. Translation here means translating your data from one protocol to the other, okay? And then the end is the application. That's the actual application that you are running. So an email, that's an application layer functionality. How it handles the messages, and it shows those messages to you as like file and the title and who's the sender, who's the receiver. All of these things are handled by your email client. Or a web browser, that's another application layer functionality. Everything handled by the web browser other than the actual exchange of data. Just how the data is displayed, where you put your commands, where you get your responses, and so on, okay? So this is the application layer. Any question about those 7 layers? No? Yes? Okay. So questions that you can be asked about this is, I give you some action that happens on a set of data, and then I ask you which layer you think is responsible for doing that action, right? Again, you do not memorize. Everything that we will do in this course is gonna be open book, not open internet, but open book, okay? So you can still have your papers where you wrote these things, or photocopied from the book, or printed from the book if you get the e-version of the book, whatever, okay? And you have that with you, and you can refer to that whenever you like. I don't want you to memorize anything. Engineers are not required to memorize except very few basic stuff. Most of them are not in this course, okay? A few basic stuffs that you need to memorize are basic things you cannot live without, right? But other than that, no need for memorization. You just need to be able to see, understand, apply, okay? How to apply what you understood, okay? And analyze, of course, okay? Yes? I don't have the online. I have access to the online book, but it's useless. I cannot give it to you. It's not a PDF file.
How can I have access to it?
I think you can buy it through the bookstore. The cover looks correct to me. I don't know about the rest. The cover looks correct. Yeah. بقول لك الكفر looks correct. Yes, that's the cover of the book. تمام. Yeah. ما هو انا هعرف بقية الكتاب ازاي؟ انا شفت الكفر بس. يس انا فاهم. هي الفكره انهي اديشن. it might be a slightly different edition. اوكي خلاص looks fine. لا 8 اعتقد. 7 في السيلبس. خلاص يبقى 7. اثبتي على اللي في السيلبس. اوكي that's fine. Okay, so I think what she has is the book. You can مش عارف. chapter 18 yes. الاثنين اللي فاتوا واحد مش من الكتاب اصلا. Okay, and chapter 1 الأول واحد بدأنا بيه. So we took so far from the book 1 and 18. And then we took something from totally, I gave you the reference, the name of the reference on the slides, تمام? We took something totally from outside the book. Okay? Any other questions يا بنات؟
دكتور عندي سؤال سريع.
اتفضلي. وليه سريع؟ اسألي براحتك.
لا عشان وقت الكلاس. بس الامتحان بيكون أصعب كذا إذا كان في البوك ولا ما له قصة؟ نفس المستوى.
يعني next. Now this slide contains a set of terminologies. Even though you can just read the slide, I'm going to go through it a little bit. These are terminologies related to the Wi-Fi. So the idea here is, in order for you eventually, what's the outcome of doing this part? The outcome is you can go after doing this part and you start. I'm not going to tell you exactly what the Wi-Fi standard says about each one of those particular topic or particular item. Why? Because there are many versions of the Wi-Fi. There is 802.11b, 802.11a, 802.11ac, 802.11n, 802.11g, And each one of those has totally different specifications for the physical layer, for the medium access control layer. I said the standard or the data link layer. The standard is only addressing the first two layers of the ISO model. So to go over all of these, we need the rest of the course, right? So I'm not doing this. I'm just telling you key features of the standard, what does it discuss, what it is concerned about, but the details of the standard, if you need it at any point, you should be able to go to the IEEE website, download it because it's available over there, start reading it, whether it's for the physical layer or for the data link layer, okay? They are two different documents typically, okay? So the idea here is to prepare you to be able to start reading the standard, but not really to give you the details inside the standard, okay? So part of that is to get used with the terminology used in this standard. And those 1, 2, 3, 4, 5, 6, those 6 terminologies, right? 7 actually. Those 7 terminologies are quite important for you to understand how the standard works, okay? The first one is very simple, the access point. You know what's the access point, right? This guy. The hub, the middle point where every single node is talking to, okay? So that's the access point. On the other side, we have something called the station. So the whole Wi-Fi is always assuming that there is an access point, AP, and there are many stations connected to that access point, right? Those stations are laptops, computers, iPads, phones that are using the Wi-Fi, okay? So these are called station, STA, and the access point, AP, the access point, okay? Those are two key factors of the terminology, okay? The basic service set is the group of stations and the access point that they are connected to. So when we say basic service set, BSS, we are talking about few nodes and the access point that they are connected to. They have to all be connected to the same access point. And the basic service point, basic service set includes the access point and all the nodes or the stations that are connected to that one. We call that the basic service set, okay? Now here at Qatar University, even though it looks like you are connected to the same access point all the time, it's not true. When you move from one room to the other or from one building to the other, your device is actually disconnecting from the one here because the signal gets very weak, and then it connects to another closer one with a stronger signal. Still, you see yourself connected to QU user, right? Or QU secure. So you don't see a change in the name of the network. Now that entails what? That entails that what's happening behind the scene is you have here a basic service set. You have another basic service set, which is AP2, for example, and some stations connected to it, right? So each one of those is a BSS, basic service set, okay? And then behind the scenes, the access point here and the access point here are connected together. And they are connected through a big network. That network might be inside Qatar University or they might be going outside and coming back to the university, right? So they are connected through a big cloud of network, right? And that cloud that connects multiple access points together, we call that the distribution system, this guy. Okay, so what's a distribution system from the perspective of the Wi-Fi standard? It's the backbone of your network, the network that connects your access points together, okay? Now, since this access point with the nodes belonging to it and this access point with the nodes belonging to it, they belong to the same owner, the same network, which is Qatar University, we call the group of those basic service sets an extended service set, this guy. But this is without the cloud, without the distribution system. So an extended service set is multiple basic service sets that are jointly talking to each other, right? That's the extended service because they belong to the same network. But this does not include the DS. The DS is not part of the extended service set, okay? Even though it connects them, but it's separate from them so in terms of definition, okay? We have two other important things, the MAC protocol data unit and the MAC service data unit. And the difference between those, remember I told you that we want to arrange our bits into chunks. We call them packets, right? Okay. So that chunk that includes your information that you want to send, plus some extra things that are called headers added to that, this whole thing is called a MAC protocol data unit. So this is an MPDU. Okay? And the information part of this, which is the piece of your file or the piece of your image, only that piece is called the MAC service data unit, MSDU. Okay? I will show it in a picture in a couple of slides. It will be easier to understand it when you see it in the picture. Okay? What remains here, so we've already covered this as well. What remains is only the coordination function. Okay? And that the coordination function is basically a terminology used in the Wi-Fi protocol to describe the coordination between the different nodes. Remember the functionality that I said, who talks and who stays silent? The control of that and the whole operation of that is called the coordination function. Okay? And in the, generally speaking, in the Wi-Fi, we have two types of coordination function. One is called point coordination function, and the other one is called distributed coordination function.
So
Okay.
the distribution system is using the coordination function for the...
La, distribution system has nothing to do with this. The coordination function is a functionality within the Wi-Fi itself. Distribution is outside the Wi-Fi. يعني هو the terminology is used in Wi-Fi, but it is a backbone that uses anything. It might, يعني in this case, the distribution function is using wired connectivity. There is a wired Ethernet between this and the next one and the next one, right? And then behind that, there is a fiber cable. That's a different standard, has nothing to do with Wi-Fi. But that whole collection of interconnectivity is called the distribution system. Okay? The coordination function is the functionality performed inside the Wi-Fi between the stations and the access point, right? To say who talks and who stays silent, right? Which is also called the medium. The algorithms that governs that is called the medium access control, MAC, medium access control, okay? There are two types of coordination functions. One is called point coordination function. The other one is called distributed coordination function. The difference between them is point coordination function, the access point controls everything. So it says everyone stay silent and then you talk now. And then after that, next half second, you talk. And if you don't want to talk, your slot is wasted. Nobody's gonna use it except the one allocated that slot, okay? This is useful in case you want to do some service guarantees. You want a guaranteed bit rate for particular user to do, for example, video streaming or something like that. On the other side, if everyone is just have a small message to send, then better to leave them to compete. Remember what I mentioned earlier about the Wi-Fi. So the coordination function does not interfere, it just leaves them, and it's the responsibility of every station to listen. Is someone in the medium now? No, then I can start sending. If someone is on the medium, then I will delay my transmission for a random time. Why random time? As I mentioned last time, because if several are trying to listen now to send, and they all hear someone transmitting, then as soon as that person stops transmission, they will all try together, which is gonna create a chaotic situation. However, if they wait, each one of them selects a random time, the chances that they will decide to transmit at the same time is gonna be very slim, because there are very slim chances that two independent random times will be exactly the same. One of them is gonna be shorter than the other, most probably, right? Okay. That they compete together and listen and start talking and so on is called distributed coordination function, while the other one where the access point says, you talk, everyone stays silent, and then you talk, everyone stays silent, that's called the point coordinated function. From the naming, it's coordinated by a single point, while the other one, everyone has part of making sure that it succeeds. They all try, they all listen, they all wait, and so on. Okay? خلاص? Time for a break because everyone... So the next couple of slides are going to be actually details on things that we have already discussed more than enough, but figures will make them look better. But this one is slightly different. Remember, I told you that the standards of the 802.11, which is the Wi-Fi technology, right, addresses only the lower two layers of the ISO model, the OSI model, which is the physical layer and the data link. However, when we look at the protocol, it's called the protocol stack because it's one layer above the other. Of the 802.11, we will see as if it covers 3 layers. Reality is those 2 are functionalities of the data link layer. Okay? But inside the standards of the Wi-Fi, they are broken into 2 pieces. One piece of them, which is the medium access control, has to do with the coordination, who talks when. Remember that? Okay? And that one is left separate from the other one because this is very hardware dependent. Okay? So depending on the type of hardware that you are using, right? The standard is different from one aspect to the other. Okay? Again, the overall methodology is the same, but I'm talking here about the actual implementation of the standard. So the standard applies the same protocol. The coordination has 2 types, point coordination function and distributed coordination function, right? And for the point coordination function, the access point says who talks when, right? And for the distributed coordination function, it's required from each node to listen first, which is called the carrier sense multiple access with collision avoidance. This one is medium access control, okay? So that part is the same as a general description, but when it comes to implementation, the implementation of the medium access control is typically implemented. Most of the functionality is hardware implemented, not software implemented, okay? So all these methodologies are gonna be implemented either on like a chip designed specifically to do the action, or you all heard about FPGAs, right? Or an FPGA which is programmed through Verilog or VHDL so that it can do that functionality. Why? Because these functionalities are very time critical, and that's why they need to implement it on the hardware itself. And this is why the standards puts this in a box separate from the remaining part of the functionality, which is the logical link control. But I remind you, both of these are data link layer functionalities, okay? Just inside the Wi-Fi, it's broken into 2 pieces. The physical stays as one piece inside the Wi-Fi standard, okay? Any questions about this? I just wanted to explain this part before we move on, because when you look inside standard document, you will see something called logical link control and something else called medium access control. So you might get confused. Are we addressing 3 layers? No, we are still addressing 2 layers. This is the data link layer, and this part is the physical layer, okay? خلاص? Okay, this is also something that I talked about earlier. This whole thing is the MPDU, right? The MAC protocol data unit. This is the packet, which is what we call the packet. Sometimes they call it the MAC packet. Why? Because even at the physical layer, we still define groups of bits. We gather them together so that we can put something like the parity check or error control or whatever. So still, we can do some data units at the physical layer, but that's not part of what we address here. We consider always the physical layer as raw data, okay? The medium access control, which is part of the data link layer, is where you actually formulate things into packets and the concept of packets appear. The information that you want to send, plus some added pieces to that information. Remember we said that DLL is responsible for what? Reliable delivery of data between one point and the other, right? So I have a transmitter, a receiver, and a single link between them, either wireless or wired. How do I guarantee that the data is delivered reliably? Reliably means correct, right? How do you do that? You need a few things. You need to figure out if an error happened or not. This is why you add to the data something called the CRC. Where did you see the word CRC before? Yes, it was a hashing function, right? Reality is CRC was not originally invented for hashing. It was originally invented for error detection. Tamam? But the same thing. What's the difference between error and the objective of hashing? What was the objective of hashing?
To compare the original
To make sure that data integrity is there.
Yes.
Nobody played with the data, right? But it can be that someone played with the data intentionally, so there is a hacker or an attacker, or it can be that nobody did anything, but the data while going from the source to the destination encountered some errors. It has some noise, and then the end result is that you didn't receive the exact data, you received a varied version of the data. But nobody was behind this. So it was not an attack. When it is not an attack, we call that error control, right? Because it's because of errors happening in the communication system. But the end result is your data was altered, right? When someone is doing it deliberately, we call that an integrity violation attack, right? In both cases, if you produce something which is dependent on that data that you can use to check whether the data has changed or not, you can achieve both functionalities. Error control, figure out if there's an error or not, and integrity observation or monitoring to figure out if someone played with the data or not, right? In both cases, it will look the same to you. It doesn't check out. That's it, okay? So CRC, the cyclic redundancy check, was actually done originally to do error control. Let me give you a quick example on what is meant by error control. Error control can mean detection only of error or detection and ability to correct. And let me give you this trivial example. You might have seen it before, you might not. Assume that I'm doing what's called parity, right? You have heard about parity, right? And let's say that my transmission includes four bits, okay, in each packet, and then I add a parity bit, right? And let's say we have 4 of those packets as well. I will tell you why 4 exactly. Okay, so one option for the parity is to do an even parity or an odd parity. What does it mean? It means that you look at the number of ones in the actual data, okay? And you add here a 1 or a 0 if it's even parity to make sure that the number of ones in the 5 resulting bits is gonna be always even. So if you have here, for example, only 1 and then 0, 0, 0, then you add here a 1, okay? Let's check a parity on another. Let's say I have a data which is 1, 1, 0, 0. Now I have even number of ones, so I add here a 0. So the total here is gonna be even. That's even parity. And this is also even parity. Similarly, 0, 1, 0, 1, then a 0. 1, 1, 1, 0, then a 1. Right? Clear how we generate the parity? Now what happens is, while transmitting this data, if any single bit here changes, right, from 0 to 1 or from 1 to 0, when you count the number of ones at the receiver, what will happen? They are not gonna add up to even, correct? Right? Because if only one of those changes, and then you receive, for example, 1, 1, 0, 0, 1, right? Now you look at what you received, you find that the total number of ones when an error happened here is gonna be odd, not even. But you know that your system is using even parity, so you know that this packet had an error or someone changed its data, right? This is for detection of change. What if I want to do correction as well? A simple idea would be to add another parity, but now you group multiple packets together, and then you add another parity in this dimension, right? And again, if you put it as even, for example, then you look in this column, right? I want to add something here to make sure that in this column is gonna be even number of ones. So I will do a 1 here, right? And what about the next column? A 1 also. The third one, a 1 as well. The fourth one, 1, okay? Now what happens if a single bit changes in this whole square, right? Let's say this bit, for example, becomes a 0. So if you check in this direction, you will find, yeah, it should be, but you find that the number of ones is no longer even. So you know that an error happened in this column. And then when you check this row, you will find that it doesn't add up as well. So you know that the bit that has changed belongs to this row and this column. If you know that, can you correct the error? How? Flip the bit, because if it was 0 and you know that this is an error, then it should have been 1. And if it is a 1 and you know that this is error, it should have been 0. So you can simply correct at the receiver as soon as you detect, right? Now this is very simple. Why? Because it relies on the fact that only a single bit changes. But if more than 1 bit changes, this system is gonna fail either in detection or in detection and correction, okay? But there are more complicated ones like the CRC that can handle multiple bit errors at the same time, okay? Anyways, the end result is this big thing, including the information that you wanted to send, as well as added pieces, to that information, including the error control part, including addressing. You say what's the MAC address of the sender and what's the MAC address of the receiver, what's the objective of that. First of all, to know whose data, who's supposed to read this information, right? Why do I care about the MAC address of the sender? So I identified the receiver, so the receiver knows that when he or she receives that packet, they need to open it and read the information. Why do I need to identify the sender? Give me a few reasons.
Like allocate the device itself.
لا, allocate any device.
يعني the one that the router will
لا, think along the concept, okay, that might be a reason, but it's not. Think along the concepts of data security and integrity. Yeah. So basically to know if this is coming from an authentic source or not. And also, non-repudiation, right? Which is you do not allow the sender to deny later that this came from them, right? Remember that requirement? So the address of the sender is also important. There's another reason actually that in many cases, if you remember, I talked to you about acknowledgement. So in many cases, I need to go back to the sender and say, I received the information correctly. If I don't know the sender, whom am I gonna send this to, right? So that's also another important reason. The last part here has to do with controlling the flow across the network, right? So something like I flag that I'm using a particular frequency, so I agree with the access point that this is our frequency of communication, or I flag that I'm currently in some of those Wi-Fi standards, you can actually use different modulation and different transmission rates. So to identify between the sender and the receiver, what is the transmission rate that we are operating on, you set a certain value in some parts of this MAC control piece, okay? So all of these gray parts, they are not your actual information. They are things added around the information to make sure that the information is reliably delivered, okay? This whole thing is called the MPDU. The piece of information only without any added parts is what we call the service, the MAC service data unit, the MSDU. Where is that? Here, okay? Remember I told you there are two things, MSDU and MPDU. MPDU is the whole thing, right? The whole packet. The MSDU is the information part of that packet only without any added stuff around it, okay? خلاص? By this, here is just a visual that shows you the, again, things that we have discussed before. Basic service set, another basic service set, the distribution system at the backbone, and these two together are an extended service set, okay? So this is just to show you those terminologies that we discussed.